How's everyone doing? Good? I'm quite surprised to see so many of you excited about async and awaiting JavaScript. I'm sorry. Now we're going to be talking about async and await and going back to the basics, talking all about how this works internally and some of the things you should keep in mind when using the task parallel library, async and await, and all of that in .NET. Some of the things that could go wrong, and we're going to see how we can mitigate that as well. My name is Filip Ekberg. I love talking about C# and .NET, and we won't have time for questions during the talk, but if you have questions afterwards, send me an email, grab me in the hallway. I love discussing all of these different things. And I do a lot of courses on Pluralsight. Some of this is also available in a much longer form. So I've taken 5 hours of content and squished it together into 45 minutes. So if you don't have a headache after this, either you didn't listen or you're just super smart. So we're going to go back to the basics and really think about why do we want to bother implementing anything that uses the task parallel library or asynchronous programming. These principles have been around for a very long time, and it's really all about avoiding unreliable applications. And I'm not referring to the fact that this is Android. The fact is that this here is not a very good user experience. The operating system notices that you're doing too much work, and in this case, it's on the UI thread, or the main thread of the application. The operating system then says, hey, you've got a lot of work going on, let's terminate the application. So we want to improve this, and we're going to do this with principles that have been around for quite a long time, but people still get this quite wrong. And we also want to efficiently consume APIs and data, be it web APIs or be it consuming file resources or database operations. We want to do that efficiently, and we want to do that correctly as well. And it's really also about leveraging all the available resources that we have, be it CPU cores to allow us to parallelize problems or consume file I/O and do that very easy as well. So really, let's boil this down into two separate things, because the task parallel library can help us do both of these different things. It really boils down to CPO versus I/O. So I can take a problem and divide that into smaller pieces, and I can use the task parallel library to say, I'd like to solve a problem and do that as efficiently as possible. Use all the cores available on my machine and distribute work appropriately. But I can also use this very neat library to consume I/O operations, reading files from disk or doing database operations or reading something off the web. But if we go back one step further, we'd like to take our application from being a blocking application and do that to a non-blocking piece of code. We want to avoid heavy lifting on the UI thread or the main thread of the application to keep it more responsive. And something you're going to hear me say quite a lot is to never block an asynchronous operation, because that can lead to deadlocks, which is extremely inefficient. And I'd like to focus on the efficiency portion of async and await as well. So really, if we go back to that Android application or UI application, we want to go from this application to something that at least tells the user that there's something going on. But we all know that if we have a spinner on for too long, the user will eventually kill the application anyways. So we can do better here as well. But that's beside the point. We're not going to talk about UX too much here. I'd like to talk about the internals, that being the task parallel library. Now, this has been around since .NET 4.5, so quite a long time. Internally, this will handle threading for you. It will use a thread pool to efficiently distribute work. Right? So the task here is for simplifying both concurrent and asynchronous operation, being parallel principles and asynchronous principle. Using one type like this here, using the task, to solve two different things can make these two different paradigms a little bit confusing. Concurrent programming or parallel programming is about taking a larger problem, dividing that into smaller chunks that we can solve independently. While asynchronous operations is also about distributing work somewhere else, but when that work has been completed, I'd like to subscribe to when that's done. So efficiently or effectively introducing what's known as a continuation. So after my work is done, send me a ping, let me know that I have something that's been produced for me, some file has been loaded, or something has been loaded off the disk, for example. So they look similar on the surface, but asynchronous programming and parallel programming are quite different, or solve different things. Now, if we do task.run, what happens is that .NET internally will look for an available thread where it can run our work, basically distributing work somewhere else. But that also means that it's going to do this as quickly and efficiently as possible. Creating a new thread in an operating system can be quite expensive, so it will reuse threads if possible. This means that you might have some thread static data still available on threads, so you should be very careful about relying on that type of thing in your applications. And also, if you do task.run in ASP.NET, you might end up doing thread pool starvation if you have a lot of requests. How many of you are doing ASP.NET? Okay, about all of you. That's amazing. So try to avoid doing task.run in your actions, for example. Effectively, what that would mean is that you would halve the amount of available operations that you can handle. There's better things to use in ASP.NET to write asynchronous and more scalable code. But doing task.run consumes one additional thread that could be used for handling one request. Sometimes you have to do it, though. So doing task.run really means that I'd like to distribute work to somewhere else. And that could be a new thread, and threads can be reused as well, which means that this is going to be a lot faster than starting a new thread manually. It will also take care of swapping between threads and ensuring that they're marked as completed and so forth. And what this also does is when calling task.run, that returns a task which you can subscribe to, introduce a continuation to say, I'd like to grab whatever work you completed. Let me know when that is done. Effectively, that's the difference between parallel and concurrent programming, or parallel and asynchronous programming. And of course, we can have two different permutations here of the task. It can either return a result, or it's just running something that doesn't produce a result. So let's jump over to Visual Studio and take a look at what this would look like if we implemented this in an application. There we go. So here, I have a simple application. I'm not going to show you the code yet. We're going to run this. It's a WPF application. Doesn't necessarily matter. I'm going to click Run here, and you'll notice that the application locks up. I can't move it around. After a little while, it says Start, the result, and End. Super simple. This is just to illustrate how async and await and the tasks work, and how we can introduce them, and how they change the flow of our code, which will also let us then experiment with how we can write this a little bit more efficiently. And efficient code means that we don't crash, we handle potential errors, and the flow is ensured in the application, that we are actually processing what we expect to as well. So looking at that click event handler, again, doesn't matter that this is WPF. I'm going to set my text box to start, and then I'm going to run some code, and I've identified that this is the problem. This is what's consuming a lot of my resources. I'm running too much code on my UI thread. If I step into this, it's quite obvious that I'm sleeping the UI thread for 2 seconds. I know that some of you are using thread.sleep to solve race conditions. Shouldn't do that. This would have been a terrible race condition if it takes 2 seconds to solve it. Anyways, so I'd like to, let's just say that this is some work that's running somewhere else. It could be an expensive hashing operation or looking up some data, whatever. Like, it doesn't matter. I'm doing thread.sleep here just to illustrate how we would solve this. Now, one of the things I see quite often is that, well, if I have some expensive operation, I'm gonna just wrap this in a task.run. What happens is that this is now going to be distributed to somewhere else, right? And effectively, here, I'm now saying that start a new thread, run work somewhere, and you're going to sleep for 2 seconds, right? So fetch a thread on the thread pool and just run this work somewhere else. Of course, now if I run this here, the application is going to behave a little bit different. It's going to give me the result immediately because now I've changed the flow of my code. So surely enough, I click my event handler, I go into the method do something, which will then schedule this work and immediately return back to the caller. That's the nature of how this works. It doesn't wait here until that's done. So if we were to then instead change the UI in here, or if we want to introduce a continuation, we'd have to change our code up a little bit here. Another thing I also quite often see is that you try to do cross-thread communications. And let's just refactor our code slightly here, because that's what we have to do when introducing async and await in the task parallel library. So let's say that instead of returning the result from this method, we could instead say, I'm just going to run that method, because that's an expensive operation, and it itself is going to be in charge of updating the UI after 2 seconds. I'm going to refactor this just slightly. which means that we have to change the signature and we have to do a little bit of refactoring to make this work. So now, if I just read this code from top to bottom, basically what I'm saying here is that I'm going to write some text in my UI, I'm going to run some expensive operation, which will be scheduled somewhere else, and immediately it's going to run the next line as well. But what do you think happens now? Is it going to update my UI with this text after 2 seconds? Possibly. Did someone say yes or no? No. It's not. And actually, nothing at all is going to happen, right? It's never going to set this anywhere. The problem here is that tasks swallow exceptions. So basically what happens here, if I run this with a debugger, this will immediately surface. It will tell me that you're trying to talk with a UI thread from a thread that doesn't own that object, but because this is wrapped in a task, I have to subscribe to when the task is done to be able to properly handle this. To do that, I have to instead introduce a continuation to fetch this. Or I also have to introduce code that would potentially actually do the cross-communication. And this is the problem with introducing the task parallel library without using async and await. But without understanding these portions, writing efficient code with async and await is really difficult. So to invoke the UI, I need to use what's known as a synchronization context. In a WPF, that's the dispatcher. In other UI paradigms, it's something different. And since a lot of you are doing ASP.NET, hopefully you're doing ASP.NET Core, is someone doing ASP.NET full framework still? Okay, about a handful. There's a huge difference between ASP.NET Framework and ASP.NET Core. They totally got rid of the concept of a synchronization context. So if you're doing, in this case here, I'd like to run some code on the UI thread. Introducing async and await means that it does context switching for you, but they totally got rid of that concept. So there's no longer a thing like the dispatcher in ASP.NET Core. But I'll get back to that in just a moment. So now I've updated my code here to say that after 2 seconds, you should invoke the UI. And again, this changes the behavior and the flow of the application. Immediately it says end, and then adds the result at the end here, which is not essentially what I wanted. Now, I improve the user experience, but the behavior and the result of the application is different, right? And again, the problem initially was that I got that exception from the task, right? So if we were to get an exception in this task here, I need some way to be able to subscribe to that. Now, the task here actually returns a task as well. So if I do task.run, that returns a task that I can subscribe to. And in this case here, I can say, well, I'd like to continue with, not this one yet. There we go. I'd like to continue with something. So this method here, this anonymous method, will be invoked after that asynchronous operation has completed. And the input is going to be the completed task. And of course, I could have referenced the run task if I'd like to, but if these are executed in different contexts, then you might not have access to that initial variable. So what happens here is that I can say that you're going to run some operations for how many seconds that might invoke the UI like I'm doing here, or if we had an exception, I'd like to be able to process that as well. Basically, if we were to throw a new exception, like this here, and not run the dispatcher, of course, I'm going to put a breakpoint inside this continuation. I'm going to click run. It's going to throw an exception after 2 seconds, and then run the continuation. Sometimes people get confused that why is it actually running the continuation when there's an exception? Well, it's because you need to be able to process potential errors. If we inspect that completed task that was sent into the continuation, it's actually faulted, and there's an exception available on that task that we'd have to handle. Now, this is where it becomes a little bit interesting, because continue with also returns a task. So if I do var continuation task, throw new exception, I'd have to subscribe to that as well. Right? And what happens if this throws an exception? I'll have to subscribe to this as well. All right? Becomes quite ugly. This is the nature of how the TPL or the task parallel library works internally. And it's totally fine that this is the way that it works. I could also subscribe to unobserved exceptions. There's on the task scheduler, you can subscribe to unobserved exceptions. However, that is only invoked once the garbage collector actually collects that faulted task. If it deadlocks or if there's something still holding on to a reference to that, it will never call that unobserved handler. So this is ugly. We don't want to do that. This here looks quite inefficient. Like I have to use a dispatcher to invoke the UI. There has to be a better approach to this here. But this illustrates that there's a little bit of problems working with the tasks. We need to be very conscious about how we work with them. If we add a continuation, we need to be very careful about what that does. If it throws an exception and we're not observing that, then we might swallow exceptions that could eventually lead to some worse problems. So we're going to leave this application for now, and we're going to introduce a way to do this a little bit better, right? We'd like to use async and await. So there's some considerations that we have to take something into considerations when it comes to the tasks. We should be very careful with wrapping code in a task.run. As I showed here, when I tried to invoke the UI, nothing happened. Like I could see that the application stopped working, but my WPF application is just a couple of lines of code. In a larger business application, finding these problems and identifying that this could potentially happen can be very tricky. I also mentioned this quite quickly, that thread static is unreliable. So because that thread pool that the task parallel library uses internally, it takes an available thread on that thread pool. If there's no threads available, it's going to schedule that work when something is available to work. However, to do that as quickly as possible, it's going to reuse threads. And threads can have thread static data. For example, in older versions of ASP.NET Core, you had the HTTP context.currentUser, a thread static variable. The problem is that that might flow across different threads or different tasks if used incorrectly. So you could potentially leak data between different tasks, which is a security concern. And we should always validate our task, right? So if there's a potential exception, then how about we need to subscribe to that? But using the task parallel library just out of the box, you had to append a continuation to each continuation, and that looks extremely ugly, and it's extremely inefficient as well. The code's going to become quite difficult to maintain if we do that. And let's instead talk about async and await. So the idea with async and await was to simplify the work with both all of these different asynchronous operations. And what they do, because there's no support in the runtime for async and await. By the time they introduced async and await in the task parallel library, the .NET runtime didn't know anything about how to work with these different concepts, which is why they're just contextual keywords. Meaning that when you add async and await in a method, they only change the behavior during compile time to that method. It doesn't do anything in runtime. It just generates a lot of code to handle all of these different things for you. So using async and await hides a lot of complexity that you don't have to write yourself. It also improves readability, but that also means that it's going to be a little bit more error-prone. You might run into issues where you have some potential race conditions or deadlocks because you're using async and await incorrectly. It's very easy to mark a method as async and using the await keyword. I simply add async and always add a task as well. You don't have to, but you should always return a task when you have an async method. Adding the async keyword simply means that this method is capable of asynchronous operations. Await means that this is where I'd like to introduce a continuation instead of that continue with. But the benefit with using await is that it does a whole lot more behind the scenes for us. So using await marks for that continuation. All the code beneath it will be executed in something similar to continue with, but it's all inside a state machine that keeps track of errors and keeps track of values and what to run next. It's super clever. It will also validate if a task succeeded or failed. If there's an exception on the task that it awaits, it rethrows that to the caller. So the caller can then also have an await and wrap that in a try-catch block. Much nicer than using the continue with approach. And a little concept that's a little bit more difficult to grasp is that when you have the await keyword, it actually returns back to the caller of that method so that it can await or that it can act on the task that's returned of this method. I'm going to try and explain this a little bit better when we look at the code in just a moment. To validate a task, we could just simply use await. Or we can append a continuation, but then remember, if we throw any exceptions inside that continuation, we're gonna end up having a problem. It might have exceptions that don't surface. As a final thing before we jump back into Visual Studio, I'd like to say that we should always use async and await together. Marking a method as async has no change whatsoever to how that code executes inside the method. You have to add specific code to actually run something asynchronously. So let's take a look at that. Let's see if we can write our code a little bit better. So I'd like to get rid of pretty much all of this here. Actually, if we go back to somewhat the initial state, I'd like to say that we're going to run something for 2 seconds, and then I'd like to change the UI to something. However, I'd like this to be non-blocking. I'd like the code to stay sort of similar, but I'd also like to say that, hey, this here is going to be capable of running some code asynchronously. Notice that I don't get any compiler warnings, or I'm getting a warning, but I'm not getting any errors. If we run this, just to illustrate a point here, it's not going to run anything asynchronously. The UI is going to lock up. There's not going to be any other differences compared to the initial version that we introduced. So this is a common misconception, that async has a greater impact. It just enables this method to do things asynchronously. Basically, it means that we should refactor the code to use asynchronous APIs. Either we can say, hey, I'd like to wrap this in a task.run to offload that somewhere else, but before you execute the next line, I'd like to await. So effectively moves that code into a continuation. Now, notice here that this is void. I'm gonna just change this to task as well. Actually, before we do that, let's just do this to illustrate what's going to happen. So now what happens is that it's going to come into this method, schedule this work to run somewhere, find a thread available on that thread pool, and run the code that we have in this anonymous method. It's going to append a continuation, take all of this code, and add that to the continue with, validate that there was no exceptions in here before it runs the next line of the code. If I run this, it's going to say start, end, and then it's going to say the result. So we have the same sort of behavior like I did with the task version of this. It's a lot less code, but it's still not the same output as I had initially. This is because if we look at run click here, what happens is that we're going to start off by printing this text. We're going to enter the method to do something. This will offload that 2 seconds worth of work, and then immediately it's going to return back here. So actually what's going to happen is that it's going to come back and run the next line. So that's what I said earlier about that when it sees the await, if it has to wait for that work to be completed, it's going to return back to the caller in this case being the click event handler. So how can I wait for this to complete before executing the rest of that click event handler? I'd have to say await this as well. However, this doesn't return anything at this point, which is why you'd like to return a task. The only reason you're allowed to do async void is because of event handlers. So in this case here, I have to mark the event handler as async as well for it to be capable to use that await keyword. Now when I rerun this application, it's going to wait for 2 seconds, and then it's going to be similar to before, but the UI doesn't lock up. So much better than what I had initially. But it's also about being efficient when it comes to async and await. I said earlier that you shouldn't just do task.run. Like if you do this in ASP.NET Core, which is where you'd get a lot of requests from users, if you consume more threads per request, then effectively you just reduce the amount of available threads that could process incoming requests from users, making your applications less scalable. It's much better if we can rely on asynchronous APIs that boil all the way down to the operating system, for example, or talk to file I/O and databases and so forth. And there's actually a task.delay that does the exact same thing as thread.sleep. So now not only did I remove that extra task that I'm executing or allocating something on the thread pool, I'm using an asynchronous API that internally doesn't spawn up a different thread or consume a thread on the thread pool, but the behavior is going to be similar. So writing efficient asynchronous principle or asynchronous code also means that we use the appropriate APIs for our operations. Now, there's one more thing that I'd like to talk about, and that's how we work with capturing these types of exceptions. Let's say that I still have something that crashes. Or I have, for example, throw new exception. What happens is that this exception, because the method is marked as async, it automatically returns a task, and that task will then have that exception set on it. So it's up to the consumer to ensure that that's not a problem. So if I wrap this in a try and catch, that's not the thing I wanted. There we go. And I put a breakpoint here, and we rerun the application. We can see that it's going to capture that exception very nicely. It got thrown immediately, and we can use normal flow. Like the code looks like it's very sequential, but internally it keeps track of state and running the appropriate thing inside what's known as a continuation. It also ensures that if there's an exception, that's being thrown back to whoever calls this. If I were to remove the await and rerun this, then the exception will be swallowed. It won't surface anywhere here. So you have to use await to validate that your task succeeded or not. Someone's probably wondering, why did I have to get rid of that dispatcher or the synchronization context? How come that this all just works? I can update the UI without an issue. Well, what happens is that we run this method from top to bottom. We update the UI, we enter this method. It's going to run some code that schedules work somewhere else. If I were to have some more code here at the top, it doesn't really matter what this here is saying. We haven't scheduled any work to run anywhere yet. This is similar to when we did task.run earlier. We have no thing or no work that's being offloaded anywhere else. So when we enter this method, we're actually going to be on the UI thread. Only that task.delay, now this is going to be confusing because this is not the UI thread. But internally, it works a little bit different, right? But let's just assume that we offload some work somewhere else that's not running on the UI thread. Now, what the await keyword also does is to ensure that it captures the UI thread or the thread that called this asynchronous operation, and after the await keyword, it will ensure that we are back on the UI thread. It will ensure internally that it marshals back to the correct thread. It uses this concept of a synchronization context to run work after it's completed. So the continuation takes care of all of that. You don't have to do anything yourself. And in ASP.NET Core, that doesn't really matter anymore because there's no longer a synchronization context. It just immediately executes whatever operation was next. So this is nice. It takes care of a lot of things for us internally. We no longer have to worry about that dispatcher, but we still have to think about, well, we're actually on the UI thread up here. So if I were to introduce some code that does a lot of work, this is still on the UI thread, right? So we can still have operations here that consume a lot of resources, which isn't necessarily that good. So I think the code looks much better. Like, it's much easier to surface errors. It's much easier to read this code and to actually maintain this. But there's some considerations in terms of this as well. There's some implications of actually adding the async and await keywords. It does a lot of stuff internally. So when marking a method as async, internally it's going to generate what's known as a state machine, something that keeps track of what's going on. Where in the execution process are we? Do we have a result available? Is there an exception? What's the original context that I executed on that I have to set the result on? So the state machine is effectively asking, are we there yet? it's not a while true loop internally. It's much smarter than that. It actually schedules itself to run on the thread pool or to schedule after work is done, so it will be immediately executed once something is done. It will handle those potential results and errors, and it also executes all the code after the await keyword. So if we take a look at a quite simple method, and I'd like to know exactly what this async keyword does to it, we're going to see that it's going to generate a state machine, and the entire method body of that method is going to be moved somewhere else. Like, it seems like that's not really an issue, but this makes debugging and reading stack traces a lot more difficult. And sometimes using the async and await keywords can eventually lead to a lot of extra code being generated that doesn't have to be generated. If you're working in IoT or mobile devices and you want to be conscious about what you write and you still want to use C#, then maybe you want to avoid unnecessary generations of state machines. So this quite simple example here, I've added the async keyword. It's added there at the top together with an await, and when I compile this, it no longer looks anything like what I had initially, right? It generates what's known as a state machine. It returns that task, right? So this here, it has to be compatible with the older runtime and the older versions of .NET, because remember, the runtime doesn't know the concept of async and await. It knows that you can return types and run methods, right? But internally, this generates the state machine and returns the task that's used inside that state machine. Right, so that's the last thing that's returned here. So if we drill into this generated state machine, what it actually does is that here we have that task, that delay that I had initially from my method. It's checking if it's completed. If it's not, it's simply going to return out of the state machine. This will be scheduled to run at a later point. And then at the bottom, it just runs the code that we had in the continuation. What's interesting here is that this entire block of code, the entire state machine, this executes on that original thread, right? So everything that's done outside of scheduling work somewhere else, it's executed on that original thread, which is how this magic works. Now, I've mentioned a couple of times that using async void is a bad idea. And the question is, why is it a bad idea? And I guess if it's such a bad idea to use async void and never return tasks, then why was this introduced and allowed in the first place? Well, let's say that we're going to jump over to Visual Studio, and I have to rewrite the code just slightly. Let's say that we throw this exception again, right? Something generates an exception in my code. Purely, in this case here, I return a task, but a lot of cases, we might just refactor code and we don't want to break the contract. We might implement something. We might implement an interface that requires something running asynchronously. This throws an exception. Now, of course, then I cannot use await, which is a little bit problematic, because that means that this line of code is going to execute immediately after I call this method or initialize that. But besides that, it looks like this code here works just the same as I did earlier. I've done my due diligence, and I've wrapped everything in a try-catch. I'm doing my Pokemon programming. We're going to press F5 and run this and see what happens. So I'm going to run this here, and we can see that I have an exception. And then immediately the application was terminated. So when there's no task to set that exception on, when the state machine that's generated for one of these async void methods sees that, well, you've not defined a task that I can set an exception on. So I'm going to do the second best thing, and I'm going to terminate your application for you. The reason that this works like this is because once this method has completed, remember, we have that asynchronous operation scheduled somewhere else. It has its state machine that's running somewhere. Then immediately after that schedule, we're back inside this click event handler, executing this code, and then we exit that click event handler. So when do something is done, the click event handler doesn't exist anymore. Right? That's the problem. We can't catch something when it's actually not inside a try-catch. So I guess this is quite a good idea because, well, at least you very quickly notice that something is horribly wrong. So we have two options to solve this. Well, we should always return a task. We should always await that. And we should also never throw in exceptions. It's easier said than done. But if we have code in, for example, a click event handler, like this here, then we have to be very careful about the code that we actually do have here. Ensure that we don't throw any exceptions. Ensure that the code that we have here is wrapped inside a try-catch. That nothing here will throw back an exception, right? So if we do that, then we'll be able to capture those exceptions again. And, I wouldn't want to drive a car that used async void. So it's quite easy to fix this. We simply change async void to async task, quite a subtle fix, right? We simply just have to do that. But it sounds very simple, but this will also then change the contract, and everyone that's using and consuming this method will now have to append and await. And maybe the interface that we're implementing doesn't allow this, which leads to more problems. So we have to be very careful about how we use async and await. Which also brings me to the next potential problem, which is extremely inefficient, and that's deadlocking. Deadlocking is much easier to run into than you might expect. A deadlock is basically when the application just hangs, or a process hangs, because it's waiting for someone else to finish first. And they're both kind of competing against the same resources. Here's an example that's not very simple. This is how you could do it. I'm going to introduce a continuation that's going to talk with the UI. But I've added .wait here at the bottom to say, let's block the UI until you've been able to talk to the UI. We run into a deadlock. So this here is not a good idea. Actually, the worst thing here is to use wait, because that's going to blow up. Now, this looks very complex. Like, who would write code like this more than me? What I do see quite often, though, is that someone calls an asynchronous method and says, hey, let's just wait for this to finish. I haven't had time to implement asynchronous flow through my entire application. So I'm just going to, for now, I'm going to use a synchronous approach. I'm going to take this asynchronous operation, and this is going to be fit very well inside my current synchronous approach. But what happens is that, as we now know, when we call an asynchronous method that's marked as async, it has a state machine internally that runs on the same thread. For that state machine to complete, it has to be able to continue on that original thread, right? So when I block that original thread, the state machine cannot work. So to avoid deadlocks, we should never use wait or the result property. We can use the result property if we are sure that the operation has completed. If you've appended a continuation, for example, either using await or inside the continue with, you may use result on that task, but it's always a code smell when I see that. We shouldn't confuse wait all with when all. This is also a very good shortcut to deadlocks. And if you're doing proper multi-threaded applications, you probably have a lot of locking, even with the new locking keyword in .NET 9 and the new implementation internally in the runtime. We shouldn't share any locks because that's also a quick way of getting into deadlocks. There's actually a nice fix. If you really want to, let's say that I'd like to not have this method as async. There we go. And I'd still like to call do something, which should appropriately now be called do something async. If I want to do that and really block, I might just mention that if I do wait, that's going to deadlock, right? But that's going to deadlock because I'm now blocking the thread that's in charge of running the state machine. What about if we move the state machine somewhere else and block the UI? All right? So now I'm blocking my UI thread, and I've moved the state machine, run somewhere else, I don't care. But we now no longer have a deadlock. But because this method is still invoking the UI, that will try to do cross-threading. And that's problematic, because we still cannot do that, right? So this is not the UI thread anymore. That's going to run inside that task.run. And that's going to throw an exception, and that's going to be monitored by the wait keyword here and going to be thrown back, and we still have a problem. So with that being said, never use wait. It's just a shortcut to a terrible application. All right, let's see here. In terms of efficiency, we can also avoid an unnecessary amount of state machines. And this is a bit of a controversy because some people say that you should do async all the way, but that doesn't actually mean that you should introduce async and await for every method that has a task. In this case here, I have an asynchronous method. Now bear with me, I'm not the best at naming. Call something called run internal async, which calls something async, which calls something internal async, which then returns some call or does async. The interesting part here is that none of them do anything inside their continuation, except the first one. If you're not doing anything inside your continuation, is there a reason to do async and await? How about we remove async and await and simply do return task? When it's compiled, the signature is going to be the same. Whoever is calling that method just expects a task to be returned. They don't care that you're using async and await. So if we want to reduce the amount of unnecessary state machines, then we don't need to await or use async and await if we don't have anything inside that continuation. But then someone's going to say, well, what about that async all the way that everyone keeps talking about? Well, we can still avoid these unnecessary async methods. However, we should always await at the top level. We should always ensure that whoever's initiating this chain of asynchronous operations always await at the top. Like I did here, right? The top level, we can have a wait there, but all of the rest could just do return task, return the call to whatever asynchronous operation they do, right? So I also want to say, in terms of efficiency, if you're trying to cancel an asynchronous operation, that's tremendously difficult. Rolling back when you've done cancellation can be quite tricky as well. Because if we have what's known as a cancellation token, which we can signal that we want to stop something, this is very normally passed into asynchronous operations. When you do task.run and you pass that cancellation token, you might assume that if you do cancel on that, it will just magically cancel your operation. But actually, passing this to a task just means that it's going to check if it's already canceled when it's starting that operation. So what we have to do is that if we have this long-running operation that processes some data, and this is what our task.run initially started, even though it used that cancellation token source, if we then call cancel on it, nothing's going to happen. Because how would this method know where to cancel or where to roll back? We have to monitor for if a cancellation is requested. We have to properly roll back data and handle when that happens. Now, I'm not a big fan of throwing exceptions as control flow, so we can use this to just in case if someone cancels, you want to exit. But we want to gracefully handle this as well. Knowing exactly when someone canceled and then handle that properly is a good idea. The final thing I want to talk about is streaming data, which is becoming a lot more popular. There's a lot of APIs that allows us to consume large resources of data, be it subscribing to a message queue in Azure to say, give me all the messages available or when they are available. There's now support for this, using what's known as an async enumerable. This here indicates that there will be data streamed of that particular type. And to consume this method, we don't have to talk too much about the implementation, but to consume this, we simply append the await in front of a for each, which basically means I'd like to grab each element out of this asynchronous enumerable one by one, handle the element, and then let me know when the next one arrives. If this is loading one line at a time from disk, for example, then it will only load the next one once you've processed that inside your for each loop. Extremely efficient way of working with streams of data. You can subscribe to queues and message buses, and this works very well. Finally, I'd like to talk about configure await, which everyone seemed to use to append to their asynchronous operations inside ASP.NET Core. A lot of operations look like this here. Await asynchronous operation, configure await false. What configure await does is to say, I'd like to continue on the captured context. The captured context in our WPF application is the UI thread. What this indicates is that the code after await, just execute that immediately on the same task you're running on I don't want to go back to that original thread. And in ASP.NET Core, since they got rid of the concept of the synchronization context, that is redundant. You no longer have to do that. It does it per default. But if you're writing libraries that work with other APIs or older versions, you still want to do this. But going forward, we can avoid doing this in our APIs. So there's a lot happening, in the terms of async and await and using this efficiently. And I've kind of gone through a lot of this in a very short time. If you want to learn more, I have a 5-hour course on Pluralsight. I released another course yesterday on secure business logic in C#, which also talks about leaking data in threads and race conditions and so forth. So be sure to check that out as well. And I do want to mention before you leave that they are doing some work on the runtime and the compiler to see how they could improve async and await internally. What if .NET and C# had the concept of async and await internally? How would that work? And would that change how the operations would process and how our code would flow and be more secure? There's a lot to consider, and hopefully you've gotten some inspiration as to how you can write more efficient async and await. Avoid deadlocking, write code that doesn't swallow exceptions, and if you have any questions about this, feel free to send me an email, leave a review. I'm going to be around, so ask any questions that you'd like to. Thank you so much for coming, and enjoy the rest of the conference.